Hi, I'm Henry, and I'll be presenting on disjointness of linear actions on Serre trees. To start off, I'll need to introduce the p-adic numbers. You may have seen these before as an ultimate metric completion of the rationals, but we'll be using a slightly different definition. So we can write any rational number as a power series over powers of p, similarly to binary or trinary expansions. The caveat that we might need to include finitely many negative powers of p. P-adics are then simply formal power series where we allow arbitrarily large powers of p. So write them as sum from I equals k to infinity. For ai, each ai is in 0, 1, 3p minus 1, and then we multiply it by p to the I. We can then define a norm with numbers with large negative powers of p are big, and numbers that only have large positive powers of p are small. Formally, we notice that k is sort of the index of the most negative power of p. Then a norm of a would simply be p to negative k. So we can add, subtract, multiply, and divide these p-adic numbers just by following the rules for formal power series you might have seen while working in power series in calculus or working in Laurent series in complex analysis. Addition and multiplication are pretty straightforward. We simply can do addition term by term or do multiplication by expanding. Division is a little bit more complicated, but we can also define it so that it makes sense over this field. Notice in particular, when we do addition, we'll need to carry the coefficients because we're thinking about these coefficients sort of as integers. This will be much more important in a little bit. Of course, now we have this p-adic norm, we can define a p-adic distance pretty easily. Simply the distance between A and B is going to be the norm of their difference. This is very similar to how we define Euclidean distance in terms of the Euclidean norm. In this case, we can think of the distance between 2 points as telling us to what extent their coefficients agree. If 2 points have a small distance, that means their coefficients have to agree up to large powers of p. If they have a large distance, maybe their coefficients don't agree for kind of smaller, like very negative powers of p. In particular, if you write these series as strings of coefficients, we can see that if a and b agree up to a certain coefficient, reflected in the norm, and c and d agree up to a certain coefficient, reflected in the norm of their difference, then a and c have to agree up to sort of the minimum index of those two coefficients. This gives us the distance between A and C is going to be less than or equal to the max of the distance between A and B and the distance between B and C. This is a sort of strong triangle inequality, and in fact, it has some pretty bizarre consequences. For instance, all triangles are isosceles, and if we have two p-adic balls with the same radius, remember that all radii will be of the form p to negative k, so there's only this sort of discretely many possible radii. We have two balls of the same radius, either they're equal or they're totally disjoint. This will come into play in a second. So p-adic balls are going to be really important to this project. So let's define some notation. Here z2 is a two-adic integer, so simply a series of no negative exponents. 1 plus 2 plus 2 squared z2 defines the ball of power series that have a 1 and a 2 to the 0 index, 1 and a 2 to the 1 index, and whatever you want afterwards. And of course, 0 is before the 2 to the 0 index. Notice that this ball has two contained balls of maximal radius. We're going to replace this first question mark with either a 0 or a 1, and raise sort of the ideal term at the end from 2 squared z2 to 2 cubed z2. You get a ball of radius one discrete step smaller. Of course, we'll have two more choices for the next question mark, two more after that, and so on, so we get to see these branching pattern of contained balls. If we draw all these contained balls, the branching pattern looks something like this. Each ball contains two maximal smaller balls, and it branches off into these two balls. Actually, just using the word branching gives us something of a clue of what's going on here and suggests, hey, maybe we should look for a tree structure. In fact, the tree structure is exactly what's going on here. What we can do is we can define each ball as a vertex within a tree. And edges will represent sort of maximal containment, where if one ball is sort of the maximal contained in another ball, it has maximal radius among all other balls contained in that ball, then we draw an edge between the ball and then the ball that contains it. So going vertex by vertex, we'll notice that each vertex or each ball contains two sub-balls or two contained balls of maximal radius, and itself is contained in one larger ball. So at least in a two-adic case, each vertex or ball will have 3 edges. Now, here's a tree using this ball notation from earlier. I think this is a little bit easier to see sort of how we get the splitting structure based on sort of we're progressively fixing more and more of these coefficients. And then here's this tree just as a tree where we forget about all the labels of the vertices. Notice it's an infinite binary tree where every vertex has degree 3. This tree actually has a somewhat interesting property. Notice if you can imagine standing at any point in this tree, the tree will look the same no matter which vertex you're standing at. And no matter where you start, it will just look like it's sort of branching off infinitely in every direction. Every vertex just splits into 2 different paths you can take. In terms of graph theory, we can find an isomorphism that takes any vertex we want to any other vertex. So every vertex sort of looks the same in some sense. So my talk has disjointness in the title, which suggests that we'll be comparing 2 things. It turns out that the p-adics aren't the only way to find a tree that we saw in the last slide. I'm now going to talk about these things that I'll call finite field Laurent series, which you probably have not seen before. So we can make a very similar series construction, but we can use x instead of p. We can define our coefficients over a finite field fp or z mod zp. We can still do addition, multiplication, subtraction, division, using the exact same rules for manipulating formal power series that we use for the p-adics. However, there's one crucial difference. Because we're defining our coefficients as elements over our finite field, when we do addition or say multiplication due to expansion, we do not have any carrying. This leads to a very different sort of structure as a field. For instance, if we look at these 2 elements that sort of look very similar and we square them, we'll see that actually the results we get are quite different. However, there is one crucial connection between these 2 fields. Namely, we can find a norm-preserving bijection between them, where we simply take p-adic power series and go through and replace every p with an x. Because the AIs will always be between 0 and p minus 1, we can just think of them as now sort of going from being integers to being inside this finite field when we move from the p-adic case to the Laurent case. Because this bijection preserves norms, it will also preserve balls. And in fact, this sort of means that we can do the exact same tree construction that we've been doing in the last couple slides, where every sort of finite field Laurent ball will have 2 maximal contained subballs, self be contained in a maximal ball, at least in the case of p equals 2. If p equals 3 or 5 or so on, we'll have sort of more contained balls. This means that if we define a tree where the vertices are balls and edges represent maximal containment, then we get the exact same tree structure that we've seen in the previous slides. This suggests these fields are similar in some sense, although not in a sense of isomorphism. For instance, clearly the p-adics have characteristic 0, while this finite field Laurent series have characteristic p. So we have a pretty interesting conundrum. In the sense of generating these Serre trees, these 2 fields are actually quite similar. They generate isomorphic trees, at least for a given value of p. However, in terms of field isomorphism, they're clearly very, very different. They didn't have the same characteristic. So one way we might look at comparing them is look at how they act on the regular tree. For the rest of the talk, we fixing p equals 2, so we can't think of this tree as being an infinite regular degree 3 tree. So you might think, well, okay, how are these fields going to act on a tree? Well, I'll explain that. The starting point is going to be special linear matrices, or matrices that form A, B, C, D, just 2 by 2 matrices that have determinant 1. For any such matrix, we can define a linear fractional transformation, as being in PSL2, where A of x will be AX plus B over CX plus D. And the determinant 1 condition ensures that these functions will actually be invertible. Now, the really amazing properties of these linear fractional transformations is that the image of a ball under one of these maps, either the p-adic or the finite field Laurent case, will be another ball. You might have seen these linear fractional transformations before in complex analysis and learned they send circles in the upper half plane to other circles in the upper half plane. In fact, a very similar thing is going on here, although I won't quite get into why it's the case. So showing these maps send balls to balls isn't too hard to show. It's just a bunch of computations. However, what's really interesting is that they also preserve inclusion in some sense. If we have some ball that sort of has maximal radius and is contained in another ball, when we apply these linear fractional transformations, either to p-adic or to Laurent case, we'll see they'll send these two balls will be mapped to two other balls that have this maximum inclusion property, either sort of the inclusion is the same or it's reversed, like the ball that was contained is now the ball containing the other ball. This means these maps not only preserve vertices of our tree, but will preserve edges as well, so acts as a tree automorphism. This explains how we get a group action on this infinite tree. We can think either about p-adic or Laurent group actions. This is an example if we're looking at the p-adic case and p equals 2, and a of x equals 3x plus 2 over 7x plus 5, and b is this ball, a 5 halves plus 2 to the 6 z2, then a of this ball will be 223 plus 2 to the 8 z2. So just thinking about these things in terms of tree automorphisms, we have the entire group of all the automorphisms of this infinite regular degree tree. We have a subgroup of group actions that come from p-adic actions, then another subgroup that come from Laurent actions. So one of the most basic questions you could ask about these two subgroups is, do they intersect non-trivially? Do they intersect a lot? Do they only intersect a little bit? Or are they totally disjoint? This is what I studied. Here it's crucial because, I mean, the trees are isomorphic, but they're actually, we think of them as two different trees. One's the p-adic tree, one's the Laurent tree. The sense we're going to think about these maps being the same is via conjugacy, i.e., when we find a relabeling of the vertices such that the action of one map looks like the action of the other map. So there's a 3 blue 1 brown video, and I think it's one of the ones in the Putnam problems. It suggests if you're faced with a hard problem, you should isolate the simplest subproblem and solve that first, which is what I tried to do. So we're going to start with affine maps where the coefficients belong to the ring of integers of these series, either the two adic integers or the actual power series over this finite field. So we don't have any negative exponents to worry about. We'll also sort of ensure that A of the x plus B map is a unit so that we can actually, so these maps are invertible. So the nice properties affine maps have is they fix the ball of integers, either Z2 or power series over F2. This means that they're also going to fix all the balls above that. They'll sort of, the other property these maps have is that they will also fix the radii of any ball. So if a ball has a given radius, the image of that ball will have the same radius. This means we can separate the vertices of our tree into these sort of below the ring of integers into these layers. So colored sort of purple, blue, green, and yellow, at least the 4 that I've shown here. We can study the permutation on each layer, which permutations of these layers will in fact be a conjugacy invariant. It simplifies things a bit, since now we're sort of, instead of having to analyze the entire action, this whole infinite tree, we can look at actions on these finite layers, which we can define in terms of permutations. In fact, analyzing these permutations boils down to analyzing the permutations that these maps induce over points of a certain finite quotient group. Either Z2 quotient out by 2CL Z2, which is isomorphic to just Z mod 2L, or Z mod 2LZ, or Z quotient 2LZ, or F2 of X modulo our quotient XDL F2 of X. To help us out, we'll define the index of the element, which is closely related to the norm. A is 1 plus 2 to JUA, or X to JUA, or A equals 2 to JUA, or X to JUA, where UA is a unit and J is greater than or equal to 1. We'll find the index of A as simply J. This is very close related to the norm, but notice for units, it's not quite the norm. We can make an analogous definition for our Laurent case. We can then use conjugation, just actual affine conjugation of functions, to reduce either studying pure multiplication group, g of x equals a of x, in the case that the index of A is less than or equal to the index of B, or we can show that if index of A is greater than the index of B, that every integer ball of a given radius, instead of every ball in the same layer, will have the exact same cycle length under these permutations that we're studying. This means we can really just study the permutations of 0 and sort of get all the information we need. This is pretty nice, since if f of x equals ax plus b, then f applied n times to 0 will be exactly atn minus 1 divided by a minus 1 times b, which again, this is the crucial property that determines what this element will be is going to be the order of A. So here we can bring in some quick number theory to related to generators of groups of units, and find formulas for the two-adic and finite field Laurent cases for the order of A. In two-adic case, we have that the order of A under sort of Z mod 2L will be 2 to the L minus Ka, where K is a constant, depends on A, but not L. In the Laurent case, we get something similar. It'll still be a power of 2, but it's very different. Actually quite, once we look at it, it's actually quite distinct. If I is the least non-negative integer, such that 2 to the I times j, where j is the index, is greater than L, then the order under x to the L of A, or sort of on the Lth layer, will be 2 to the I. Notice that in the p-adic case, the order increases exponentially as L increases. While in the Laurent case, the order increases only linearly as L increases. This will imply some sort of disjointness. In particular, if we have a p-adic map and a Laurent map that we expect to be in conjugate, we can look at very, very large L and see that so the maximal cycle length of these permutations on a given layer grows exponentially in the Laurent case and linearly in the exponentially in the p-adic case and linearly in the finite field Laurent case. So for very, very large L, it'll certainly be true that the p-adic case will have longer cycles than the Laurent case. And therefore, these two maps cannot be conjugate as free automorphisms. This leads to our first disjointness theorem. If we have two affine maps, one over the p-adics and one over finite field Laurent maps, and their actions in on their respective Serre trees are conjugate, then in fact, A1 and A2 are both the identity map. For the affine case, these two subgroups intersect as little as possible. They intersect just at the identity. But we're not really interested in affine maps. We're really interested in SL2C. We've had some nice results, but really it's time to go deeper. So the nice thing about these SL2 maps is that they still have to fix the ring of integers. It's either Z2 or sort of power series over F2. However, they no longer fix radii. So it could be a sort of point above the ring of integers, or sort of with a larger radius gets moved down to be below the ring of integers once we apply these maps. However, they'll still have to fix the distance from the ring of integers. So we still get a layer structure. So now these layers each have only 3 times the power of 2. They'll have that number of points, and they sort of go out from the ring of integers. The nice thing is we can still use permutation analysis. If we just look at the first 3 points, sort of adjacent to the ring of integers, we see that there are 6 possible ways that it can be permuted. I'll use type 1, 2, 3, 4, 5, and 6. You can actually split these into 3 conjugacy classes. Type 1 I like to think of as the everything is fixed case. Type 2 and 3 are sort of the rotation, or I think was the windmill case. And types 4, 5, and 6 are the swap cases. We can actually realize all of these cases with matrices, which I have depicted here. As it turns out, in some sense, type 1 is the worst case. For any other case, we can conjugate our matrix, or conjugate the centriotomorphism into a very specific form. If M isn't of type 1, we can find M prime, if we conjugate to it, of the form 0, A inverse, and B, where A and B are in the ring of integers, and A is a unit, so is invertible. Notice that M prime, based on definitions of the last slide, is either going to be type 3 or 6, depending on whether or not B is a unit. So notice if M prime is type 3, i.e. the rotation case, we actually want to look at M prime cubed, since that'll sort of move everything back into the fixed case. If M prime is type 6, or the swap case, we'll look at M prime squared, because that'll sort of undo the swap and put us back to an everything is fixed case. We then have maps that actually do, at least for points below the ring of integers, will fix the radii of points, or radii of balls. I've just written out here what M prime squared and M prime cubed look like. These aren't affine, but in some sense they're good enough that we can do the same kind of analysis as before. So I did this analysis. It's some computations you can go through. I also developed a computer program to help me sort of just compute these things quickly so you can look for patterns. We can actually see we get a very similar pattern to before. The orbit length of 0, or sort of the 0 point in every layer, 0 plus 2 TLC2 under M, increases exponentially with respect to L in the p-adic case. On the other hand, the order of 0 plus x to the L, and then F2 of x. In the Laurent case, the orbit length of any point is going to be bounded above by 2 to the L, where L is sort of the distance from the origin in the Laurent case. Just to repeat that, in the p-adic case, we have sort of exponentially growing cycles. Well, in the Laurent case, every cycle has length that's bounded above by this linear constant, 2 to the L, or 2 times L. What this means is that we can do the exact same argument before, where if we increase L large enough, if we get sort of far away from this fixed integer point, then in fact we'll be able to find a very long cycle in the p-adic case that won't show up in the Laurent case. These two maps can't possibly be conjugate, unless in fact M1 or M2 to sort of matrices we're starting with have finite order, in which case we don't get this sort of growing cycle length at all. So this is the theorem. If we have a group action from the p-adic case and a group action from the Laurent case, so for a special linear 2 and then the coefficients in a ring of integers, and their actions are conjugate, then M1 and M2 have to have finite order as matrices. So this might seem like it doesn't actually narrow things down very much, but in fact it does, because there are very few matrices that actually have finite order. In fact, they actually are the kinds that we saw in sort of type 1 through type 6 slide that I had, where there's just be a pure rotation that puts everything back where it started after 3 steps, or a pure swap that sort of puts everything back after 2 steps. So these are actually the one exceptional cases, and I was pretty excited to find these. After all, it's nice to find an example of things actually work out. So we have M2 and M3. These are just 2 examples of sort of the pure swap and a pure rotation maps. Now, if you are familiar with group theory, you might think, well, wait a second. These 2 elements actually will generate all of the special linear group in the p-adic case. So couldn't it be that because these 2 are conjugate to some Laurent counterparts, so we can sort of get everything just by using these as generators for our group? Well, not quite, because they're actually they are conjugate, but they're conjugate by different maps. So when we sort of multiply them by each other, the conjugacy will get kind of messed up. And this is sort of the root reason of why maps in a p-adic and Laurent case are not conjugate. So we have an answer for affine maps and maps that form SL2, where all the coefficients are in the ring of integers, and p equals 2. Obviously, there's a lot more questions we could ask. For one thing, what if p is greater than 2? Well, the reason I started the p equals 2 case is that coefficients are very easy to describe. Either they're 0 or they're 1. And in fact, we know that the first non-zero coefficient has to be 1. When p is greater than 2, these coefficients could be other units not equal to 1. For instance, in p equals 5, they could be 1, 2, 3, or 4. This will make the computations quite a bit more complex, just in terms of having to write them down. But my intuition is that this won't really actually change any things. After all, we still sort of have the exponential versus linear growth in terms of the order of a given element. So I expect that we see a very similar pattern. And in fact, in this case, the group actions would still be very disjoint, with the exception of the fixed points. The other question we can ask is, well, okay, let's look at a bigger sort of subgroup of automorphisms, or a bigger group space of group actions. 2 examples might be SL2Q2 or SL2F2X, where now we allow sort of negative exponents, or GL2Q2 or GL2F2 of X. Here, the primary stumbling block is that we can find maps that don't have any fixed points at all, or find maps that sort of have very different fixed points. In particular, maps that don't have any fixed points at all do have a specific structure where you can find sort of a line in a tree to sort of slide vertices along. But so there may be some way we could utilize this structure, but just in the basic sense of what we've done before, we won't be able to use a sort of layer permutation analysis trick. So we'll need to come up with something new. The other question is, lastly, what other discrete valuation fields, which include the p-adics and these finite fields finite field Laurent series that I've been studying? I personally haven't thought of any other fields myself, but if you have ideas of fields I should study next, I'd love to hear about it. Yeah, so that's my presentation. Thank you so much for listening, and here are my references. If you have any questions, you can contact me at henry_talbott@brown.edu. I'll just go to the top so you can see my name spelled. Again, thank you so much and have a great day.